Quantum physics is an enigma. It's a world where particles can be in many places at once. They can also be linked across vast distances. Imagine throwing a pebble into a pond and seeing ripples everywhere simultaneously. That's the beauty and mystery of quantum physics. This essay will take you on a journey into this strange realm. We'll explore concepts that defy common sense, from particles existing in multiple places to being interconnected across light years. Quantum physics challenges our understanding of reality. It makes us question the nature of the universe. How can something be in two places at once? How can two particles be linked with no physical connection? These questions are at the heart of quantum mechanics. We'll start with what quantum physics is and delve into its core concepts. Hold on tight, it's going to be a mind-bending ride. Quantum physics is the study of the smallest particles in the universe. These particles include electrons, protons, and neutrons. It's the science that explains how these particles behave. Unlike classical physics, which deals with the macroscopic world, quantum physics operates at the atomic and subatomic levels. In classical physics, objects have definite positions and speeds. But in quantum physics, particles behave differently. They do not have definite positions or speeds until they are measured. The term quantum comes from the Latin word for how much. It refers to the discrete units of energy that particles absorb and emit. Quantum physics has revolutionized our understanding of the universe. It has given us new technologies like lasers and transistors. Classical physics is what we encounter in our everyday lives. It deals with the laws of motion and gravity, discovered by Newton. Objects have fixed positions and velocities. If you throw a ball, you can predict where it will land. This predictability is the hallmark of classical physics. Quantum physics, on the other hand, is unpredictable. It deals with probabilities rather than certainties. A particle could be here, there, or anywhere. Only when we observe it does it choose a position. This uncertainty is a fundamental aspect of quantum mechanics. In classical physics, objects are independent of each other unless they interact. But in quantum physics, particles can be entangled. This means they are connected in such a way that the state of one affects the state of another, no matter the distance between them. Superposition is a core concept in quantum mechanics. It states that particles can exist in multiple states at the same time. Imagine flipping a coin. In classical physics, the coin is either heads or tails. In quantum physics, it can be both heads and tails simultaneously until you look at it. Erwin Schrödinger illustrated this concept with a famous thought experiment. Imagine a cat in a sealed box with a radioactive atom. If the atom decays, it triggers a poison that kills the cat. If it doesn't decay, the cat lives. According to quantum mechanics, until the box is opened, the cat is both alive and dead. This is the paradox of superposition. This thought experiment highlights the strange nature of quantum mechanics. Superposition is not just a theoretical concept, it has practical applications in quantum computing. In a quantum computer, qubits can be both 0 and 1 simultaneously, allowing for faster calculations. Section 5. Heisenberg's uncertainty principle. The Heisenberg uncertainty principle is another fundamental concept in quantum mechanics. Proposed by Werner Heisenberg in 1927, it states that you cannot simultaneously know the exact position and momentum of a particle. The more precisely you know one, the less precisely you know the other. This principle challenges the deterministic nature of classical physics. In classical physics, you can measure both position and velocity with great accuracy. But in the quantum world, this is not possible. The act of measuring one property affects the other. The uncertainty principle has profound implications for our understanding of the universe. It suggests that at a fundamental level, the universe is governed by probabilities rather than certainties. This probabilistic nature is a key feature of quantum mechanics. Section 6. Quantum entanglement. Quantum entanglement is one of the most intriguing phenomena in quantum mechanics. It occurs when two particles become linked in such a way that the state of one instantly affects the state of the other, no matter how far apart they are. Einstein famously referred to this as spooky action at a distance. To understand entanglement, imagine two particles that interact and then move apart. If you measure the state of one particle, you immediately know the state of the other, even if it is light years away. This instant connection defies classical physics, which says that information cannot travel faster than the speed of light. Entanglement has been experimentally verified many times. It plays a crucial role in quantum computing and quantum cryptography. Section 7. The double-slit experiment. The double-slit experiment is a classic demonstration of wave-particle duality. It shows that particles like electrons can exhibit both wave-like and particle-like properties. In the experiment, electrons are fired at a barrier with two slits. If one slit is open, the electrons form a pattern behind the slit, as expected. But if both slits are open, the electrons form an interference pattern, like waves. This suggests that each electron passes through both slits simultaneously, interfering with itself. This wave-particle duality challenges our classical understanding of particles. In the macroscopic world, objects are either particles or waves, not both. But at the quantum level, particles can exhibit properties of both, depending on how we observe them. Section 8. Wave-particle duality. Wave-particle duality is the idea that particles can exhibit both wave-like and particle-like properties. This duality is a cornerstone of quantum mechanics. It was first proposed by Louis de Broglie, who suggested that particles like electrons have wave properties. De Broglie's hypothesis was confirmed by experiments like the double-slit experiment. These experiments showed that particles can create interference patterns, a characteristic of waves. But when observed directly, these particles behave like discrete entities. Wave-particle duality is not limited to electrons. It applies to all quantum particles, including photons, protons, and even larger molecules. This duality blurs the distinction between particles and waves, challenging our classical understanding of the physical world. Section 9. Quantum computing. Quantum computing is a revolutionary technology that leverages the principles of quantum mechanics. Unlike classical computers, which use bits as the basic unit of information, quantum computers use qubits. A qubit can exist in a superposition of 0 and 1, allowing it to perform multiple calculations simultaneously. This superposition gives quantum computers a significant advantage over classical computers. They can solve complex problems much faster. For example, a quantum computer could factor large numbers exponentially quicker than the best classical algorithm. This has profound implications for fields like cryptography, optimization, and drug discovery. Quantum entanglement is another key feature of quantum computing. Entangled qubits can perform coordinated operations, further enhancing the computational power of quantum computers. Despite their potential, quantum computers are still in their early stages of development. Section 10. Philosophical implications. Quantum physics has profound philosophical implications. It challenges our classical understanding of reality and forces us to reconsider fundamental concepts like determinism, causality, and the nature of existence. One of the most debated topics is the role of the observer in quantum mechanics. The act of observation affects the state of quantum particles. This idea is central to the Copenhagen interpretation, which suggests that particles exist in a superposition of states until observed. This raises questions about the nature of reality. Does reality exist independently of our observations, or do we create it by observing? Quantum physics also challenges the concept of determinism. In classical physics, the future state of a system can be predicted with certainty if we know its current state. Section 11. Real-world applications. Quantum physics is not just a theoretical science, it has real-world applications that have revolutionized technology. One of the most significant applications is in quantum cryptography. Quantum cryptography uses the principles of quantum mechanics to create secure communication channels. It ensures that any attempt to eavesdrop on the communication will be detected. Another critical application is in the field of semiconductors. Quantum mechanics explains the behavior of electrons in semiconductors, leading to the development of transistors and integrated circuits. These components are the building blocks of modern electronic devices, including computers, smartphones, and many other gadgets. Quantum physics also plays a crucial role in the development of medical imaging technologies. Techniques like magnetic resonance imaging, or MRI, rely on quantum principles to create detailed images of the human body. These technologies have revolutionized medical diagnostics and treatment. Section 12. Summary and reflection. In this essay, we've journeyed through the strange and fascinating world of quantum physics. We began with an introduction to the mysterious nature of quantum particles. We then explored core concepts like superposition, the uncertainty principle, and quantum entanglement. We also looked at the double-slit experiment and wave-particle duality. We discussed the revolutionary potential of quantum computing and its real-world applications. Finally, we delved into the philosophical implications of quantum mechanics and its impact on our understanding of reality. Quantum physics challenges our classical notions and opens up a realm of possibilities that were previously unimaginable. Quantum physics helps us understand the universe at its most fundamental level. As we continue to explore this quantum realm, we will undoubtedly uncover new mysteries and technologies that will shape our future. The journey may be challenging, but the rewards are limitless.